Good morning, everyone. We are Group 15, and the topic that was assigned to us is how GPUs are used in data processing or data science. But first, what is a GPU? A GPU, or a graphics processing unit, is a dedicated microprocessor. It can also be thought of as a specialized CPU that specializes in multitasking. We are often familiar with GPUs being called as graphics cards or video cards. But in layman's terms, they are the same. And they are both used for graphics or video rendering or anything that is related to graphics. Now, I think you're probably wondering what is the difference of GPUs compared to CPUs in terms of architecture. CPUs have fewer cores, while GPUs are composed of hundreds more smaller but specialized ones. The CPU is designed to do sequential or serial computing, while GPUs are designed to do parallel computing. A visual aid can be seen here that explains serial and parallel computing. Serial computing, as you can see, it can only process data one at a time, and at parallel computing, it processes data simultaneously. Then, the CPU excels at low latency operations such as swiftly retrieving data from the hard drive, while the GPU excels at operations that require high throughput such as rapid graphical and mathematical operations. Throughput, it is the amount of data a system can process in an amount of time. Okay, now we are moving on to the brief history of GPUs. Late 1970s up till to the early 1980s, dedicated graphics hardware started to emerge in early computer systems like the Atari 2600 and the NES. 1995, NVIDIA released the NV1, one of the first dedicated graphics processing units designed for 2D and 3D graphics acceleration. 1997, 3DFX Interactive introduced the Voodoo graphics chip, which popularized 3D gaming on personal computers. And during 1999, NVIDIA released the GeForce 256, marketed as the first GPU and featuring hardware that has transform and lighting capabilities.
Hello, for today we will be deconstructing a GTX 580. We will unscrew these 4 screws holding in the heatsink of the GPU to the PCB. Then after that, we can simply pop off the heatsink from the PCB. Be careful, there is still a wire connected over here. So we will remove the fan connector. Here we have the heatsink of the GPU with the GPU chip being here and the VRAM thermal pads connecting on this side.
Now, we'll talk about the different parts of the graphics card. First, we have the video RAM or the frame buffer. Not only does it serve as the buffer between the CPU and the display, but it also serves as the memory where data is being processed by the GPU is stored. This is the VRAM.
The VRAM chips on covered by these thermal pads. This is the GPU chip itself covered in thermal paste.
And we have 2 standards for VRAM. We have the GDDR, which is the graphics. It's like DDR in RAM, but more specialized in GPUs to have more parallel processing power. And we also have high bandwidth memory. Next is the voltage regulator module, or VRM. These are composed of capacitors that control the voltage of the electricity passing through the GPU's components. Next, we have the fan interface, where the fan of the GPU is connected. It is used for cooling purposes. Pwede uminit ang GPU.
The fan connector.
And this here is a PCI Express, where the GPU is being connected to the motherboard by the PCIe bus. We have this part is called the SLI or the NVLink in NVIDIA GPUs. SLI means scalable link interface, and newer versions of the NVIDIA GPUs, this is replaced by what we call NVLink. This part allows different GPUs to be connected together. But in the latest NVIDIA GeForce RTX 4090, this part was removed and was replaced by the latest version of the PCIe Generation 5 because NVIDIA deemed that this part is sufficient enough and it is fast enough that it renders this part useless. We have previously mentioned that there are hundreds or thousands of cores found in the GPU, and two types of these cores that we can find in the core in an NVIDIA GPU are what we call the CUDA cores or the tensor cores. CUDA stands for Compute Unified Device Architecture. It was first introduced in NVIDIA's Maxwell architecture in 2014, and they exist in large numbers inside NVIDIA's GPUs. And they specialize in graphics processing. However, with the use of the CUDA platform, it is possible to also use these cores for computational processing and parallel processing. Next, we have the tensor cores. Tensor cores were introduced in 2017, but it became more widely available in 2018 together with the release of NVIDIA's Turing architecture. These cores are more suited for AI and machine learning purposes because compared to the CUDA cores, they are much faster at computing. However, they sacrifice their accuracy. So, bale, compared sa CUDA, mas mabilis mag-compute si tensor cores, however, less accurate. CUDA is slower, however, more accurate. Depending on the NVIDIA GPU, these two types of cores exist in different numbers. In consumer GPUs, there are a lot more CUDA cores compared to tensor cores, but in NVIDIA's data center GPUs, we can see that there is a balance between these two cores. We have previously mentioned that we can find two types of cores in the NVIDIA GPU. First, the CUDA cores and the tensor cores. But how exactly can we take advantage of these cores? Kaya meron tayo CUDA platform. The CUDA platform or the Compute Unified Device Architecture platform was developed by NVIDIA in November 2006. It is a parallel computing platform and application programming interface model, which allows the developers to access the instruction set of their NVIDIA GPUs. Ano ibig sabihin nun? Well, basically, it enables the developers to utilize their GPUs for more general purpose computing and tasks rather than just graphics processing and physics processing. How can we use this CUDA platform? So, NVIDIA has provided extensions for CUDA in the following languages: C, C++, and even Fortran. As of now, CUDA has also provided support for other languages like OpenCL and also with some Python libraries, which means that for programmers who are already familiar with these languages will have an easier time using CUDA. One of the main features of CUDA is what is called kernels. These kernels are basically user-defined functions within the program that takes advantage of the GPU's cores. When the program encounters these kernels, the GPU cores will divide this function into subtasks, and the GPU cores will execute them simultaneously.
So in today's age, GPUs are used in various fields such as computer graphics and gaming, high-performance computing, and deep learning AI. As for computer graphics, as we all know, GPUs are used commonly in gaming. So GPUs are used to render graphics. So better GPU you have, better graphics you have. Next would be deep learning and AI or artificial intelligence. So GPUs handle the massive matrix operations and parallel computations such as image and speech recognition, natural language processing, and autonomous vehicles. One example would be Tesla for their self-driving cars. And next would be high performance computing. So for high performance computing, GPUs boost HPC environments for scientific simulations, weather forecasts, and computational fluid dynamics, and other computationally intensive tasks. As for the field of data science, GPUs excel in parallel processing, which means that they can process as many computations simultaneously. So compared to traditional CPU-based computations, GPU computations are faster. And through this, data analysts can process larger data sets and perform complex analyses more quickly. So first example would be the GPU accelerated data analysis. So for GPU accelerated data analysis, GPUs can accelerate analysis tasks such as data cleaning, transformation, and visualization. For example, tools like Rapids, built on NVIDIA's CUDA platform, leverage GPU acceleration to significantly speed up data manipulation tasks in data pre-processing pipelines. One real-life example of this would be for weather forecasting. So GPUs accelerate numerical weather prediction models by parallelizing calculations involved in simulating atmospheric dynamics, cloud physics, and other meteorological phenomena. So GPUs help render high-resolution forecasts and more quickly and accurately. Next would be the machine learning model training. For learning model training, especially in deep learning models, it involves pre-processing large data sets and performing numerous matrix operations. One real-life example for this would be autonomous vehicles like Tesla. The training of AI algorithms for autonomous vehicles enable them to process sensory data and detect physical objects and make driving decisions in real time. So through this, they accelerate training tasks like object detection, semantic segmentation, and reinforced learning. Last would be the GPU accelerated visual data visualization. So for data visualization, it is essential for understanding patterns and insights in large data sets. GPUs can accelerate rendering and visualizing data and enabling real-time interactive exploration of complex data. Data visualization helps understand patterns, trends, and relationships with large datasets. One example for this would be urban planning. So for urban planning, GPUs accelerate the visualization of urban development scenarios, such as traffic simulations and environmental impact assessments. So they parallelize rendering tasks involved by generating 3D models, simulating traffic flow, and visualizing environmental factors. So that is it for the data science in GPUs.